Now we'll see this example, and with this example I am going to explain you reordering of instructions. First of all, we take these 4 instructions and we see the pipeline execution. Later we will reorder it because you understand the reason for that. Example, let's say the first instruction is load R1 0 of R0. Let's say this is the instruction flow: fetch, decode, execution, memory, write back. Then second instruction, this is I1, this is for I2, this is for I3, this is for I4. Now we'll see what is the problem with this execution. So this is actually wrong. The reason that R1, if you see the dependencies between add instruction and load, so there is no dependency between this load and this load, because this load is loading. First we try to understand the meanings of these instructions. We are loading into register R1 the value which is at memory of 0 plus R0. Okay, so R0 is some register. For easy understanding, let's say content of R0 is 100. Okay, so what is going to happen is, this is your main memory. Because of this instruction load R1 0 of R0, so R0 is 100, right? Content of R0. So 0 plus 100, 100. So we are going to main memory of 100, and whatever the data, let's say X, then X we will be writing into R1. That is the meaning of this first instruction. Second instruction is getting some data from 4 plus R0, which is nothing but 104, right? Because R0 is still 100. So 104's content is Y. Then this load instruction is loading R2 with Y, right? Because value at 104. Now then later add instruction is adding R1 and R2 values which are nothing but X plus Y. So finally we are adding X plus Y, correct? And we are storing it in R3. Now there is a dependency. Why? Without completing a load instruction, we can't do add, right? Now you require R1 and R2 at what stage? At earliest, in the execution stage, right? That means here you require R1 comma R2, remember it. So finally you want R1 data, R2 data here. This is the earliest. Now what is the earliest time you get correct data because of load instruction? Maybe after write back, correct? This is the only place you have correct data at register R1. In all other places R1 is not updated, correct? Now, and one more thing, but if you cleverly plan, in the memory stage itself we are getting the data which has to be written into R1. To write into R1 whatever the data is required already available at memory stage, right? After memory stage. Now we try to use forwarding. Without forwarding we can't do, right? So without forwarding, what is going to happen? Data available is here, but data requirement is here. That's why it won't work. Similarly, one more data R2 is available here, but you want here. So we have to go for forwarding. Let us try forwarding. To do forwarding, I connect this memory write back buffer to this one, right? Finally, we should cover like this. See, here already we have data. Sir, we don't have data, right? Because you said after write back stage we are going to get the data. See, this is your register file. This is your register R1. So because of this instruction, after 5th clock cycle, 1, 2, 3, 4, 5, after 5th clock cycle, we are writing X here. But before that itself, X value is already fetched, right? So after memory stage, already X is there, but that is not written in register R1. So using cheat sheet, what we do is we simply forward this X, because already that is there in this buffer, like this, right? That means connect buffer of memory write M comma W, let's call this as MW buffer, and this is DE buffer. By properly connecting using the hardware MW buffer and DE buffer, we can bypass the data, right? It's not a big deal, right? But the thing is R2, because you require here for I3 instruction R1 and R2. You got R1, but how do you get R2? Where is R2 data? If you go in the straight line way, that means without any cheat sheet, R2 is available here, but the content of R2 is already available in the memory and we already got it, right? So here, this is the earliest point where still we can manage and get the data, right? So what we do is, in this buffer already we have Y, which just we got from memory, then we have to forward like this. But this is forwarding backside, that means it is backwarding. That is not possible because timeline. See, we have data at at end of the 5th clock cycle and you want to forward it to 4th clock cycle. That means 5th unit data at 5th unit you want to transfer to data otherwise position at 4th clock cycle. That means you are traveling backside in the time. That is not possible. So what to do then? We have to definitely wait. Here what I want to tell you is to execute this instruction, forwarding will not be possible, right? So what is the solution? Very simple. Stall the cycle. Assume that let's say somehow your hardware can detect that there is a dependency and let's say somehow it is stalling the pipeline. So in the next time what we do is we don't execute instruction. That means we don't fetch the instruction. Then the next instruction we fetch here, let's say. So instruction fetch again here, then decode, assume like that, let's say it is possible, then execute, then memory and write back. See this story now? This is add instruction. Now if you do like this, now same story, at execution time you require R1 comma R2. Now it's not a big deal. Even you don't really require to take the forwarded data, right? Without forwarding data also, see already connections are there, but I am not taking the forwarded data because already data is available in the original line, correct? So that means already the data is available in the register file. So R1 is need not to be forwarded, right? Second thing, but R2 data should be forwarded. Yes, we forward like this. See, already R2 data is available here. I forward like this. Okay. Now here, of course, connection will be there, but that data need not to be taken, right? This forwarded data need not to be taken. The multiplexer directly chooses. That means we get the data from original register, not a problem. You understand my point? What I'm saying? What I'm saying is, though you have connections, okay, I take the data from here, but I don't take the data from here because I have data already available in the correct data available in this my exact flow. That means this straight line flow, right? So you don't require forwarded data. Of course, if you take also not a problem. So how you implement your hardware is important. Understand? Now it is like I'll give you an analogy. Example, let's say you are writing one exam and someone is selling answers, okay, answers. Otherwise someone is selling the questions before the exam. So you have two possibilities. You can get the questions in the exam hall at 9 o'clock, let's say there is exam, but 8 o'clock someone is giving you questions. There are two ways you can get the questions. But what happened? Someone is ready to give you questions at 10 o'clock. What is that? I mean, is it really required? No, right? Of course you can take them, but 9 o'clock itself already you have questions, right? Because you are writing the exam. Then it would be good if someone gives us at 8 o'clock. In the same way, here also, you have a possibility to have questions, right? Like this, from other source. But this source is also good, right? Original source. That's why there is no problem. That's what I'm saying. So finally, using the forwarding, we can execute this instruction correctly. Now we'll see load instruction, the fourth one. Load R4 8 of R0. So it is depending on only, see, we are loading into R4, but R4 is a different register that is not at all related to anything. Then there is no data dependency. Happily we can execute it. There will not be any problem, right? This is about executing these 4 instructions. Let me summarize. As it is, if you want to execute, that is not possible, right? Then at least we have to use forwarding. So finally in this model, to execute all these instructions correctly, forwarding is required. Second one, but simple forwarding is not sufficient. Though you are doing forwarding, but at least still there is a stall, right? We have to stall the pipeline also. How many units? 1 unit, correct? That is one thing. Now third one, if I reorder these instructions, am I going to get any benefit? We will see. So how I reorder is, this load instruction is not at all depending on these 3 instructions, right? Why don't you load R4 first? Because that is not at all related to these instructions. Then meaning will not be changed, correct? So what I do is, I write load instruction here. Remember one thing, whenever you reorder the instructions, okay, first of all I write add R3, R1, R2 here. Add R3, R1, R2. Be careful, when you reorder instructions, the meaning of the program should not be changed. Since this load instruction is loading a register R4 which is not at all related to these three instructions, there will not be any problem. And especially we are taking the data from 8 of R0 where R0 is not at all modified, there will not be any problem, right? So now if that is the case, so can I execute these instructions without stalling the pipeline? We will see. Okay. Now already load R1 is done, right? Just keep that in the mind. Remaining instruction should be rewritten. So now let me execute this load instruction, second load instruction. Okay. So I1, this time I1 is load, I2 is load, I3 is load, I4 is add. Okay. Let us start. I2 is load, then 1, 2, 3, 4, 5. Since it is not depending on anything, happily we can continue, right? So fetch, decode, execute, memory, write back. Now if you see the details, finally in the memory stage we are getting the value, that whatever the value we are getting from the memory, that we are writing in the write back stage. That means R1 is updated in the write back stage, you remember. Okay. Now we will come to third load. That third load is also independent. We can happily do it. Fetch, decode, execute, memory, write back. Okay. Now, see, if you have time and if you have patience, because you are a student, right, you have to practice. Then what you do is, in every stage, what are you doing? What kind of registers you are reading? What kind of registers you are using? Everything you simply write. Already I told you which buffer contains what, correct? So if you write it, it would be good. But in the GATE exam, we have to answer the question, right? So if you write neatly everything, like in this stage, what are the parameters you want? For execution stage, you require, here we have to compute effective address. Effective address formula, this component plus this component. Already in this buffer, 0 is available, R0 is available. We have to add 0 plus R0. That means 0 comma R0 will be given as input to execute stage. Correct? So that kind of things you have to write, but of course not required, right? Without that also we can solve. You see, I1 is load, I2 is load, I3 is load. Correct? Now dependency thing comes, which is add, right? Fetch. Let me fetch here. Let us try. Without stalling the pipeline, is it possible or not? Now decode. Okay. Then execute. In the execute stage, we will be adding R1, R2. Correct? That R1's content, R2 content already I am taking from decode stage. Correct? So R1, R2 are available for me. Now the question is, this R1 and R2, are they correct? By this time we will see. By this time instruction number 1 is completely done. Then this R1 will be properly updated. No problem. Now where you require R2, right? Anybody is modifying R2? Yes. So by that time R2 is not properly updated, right? In the write back stage R2 will be updated. But before that itself you are connecting this R2 to execution stage. Then this content of R2 which you have got in the decode stage is wrong. Yes. Then you have to go for forwarding, right? So what I want to tell you finally here is fetch, decode, execute, memory, write back. Here we have to do bypassing, right? How to bypass R2? Where is R2's availability? We have R2's availability here, you see. In the after memory stage already we got the value to be stored in R2, correct? That you forward here. Okay. Now finally, because of this cable, the right data will come and the wrong data will be ignored, right? So that is the way your hardware will be designed. Now after that execution will be done, memory and write back everything. So what I want to tell you is, with one data forwarding, we can execute these instructions by reordering the instructions. Finally you realize that if I reorder the instructions, then sometimes pipeline stalls can be avoided. Sir, why we have to avoid the pipeline stalls? What does it mean? What is the meaning of pipeline stall? Every pipeline stall, when you are stopping the pipeline for one unit, then you will be decrementing the performance, right? Example, if no stall is there, then everyone is working full-fledged. Suddenly, example, you see this one. One is, just take the chapati example or roti example. Someone is making balls here, ball. Here someone is making, pressing. someone is frying, correct? Suddenly you stopped this fellow to not to, example, you stopped him for 3 units of time. So in 5 minutes of times, you stopped him not to make the balls. Then what happens? If he cannot make the balls, then in the next levels, this fellow cannot press the balls because balls will not be available. Then in the later stages, so the third unit also will stop functioning, correct? In that way, everyone will stop working for some time. So because of that, performance will be affected. Then the production of rotis will not be for every 5 minutes one, right? So suddenly what happens if there is a stall, then suddenly for some period of time, so no chapatis will be produced. But later when you start again this fellow, that means the first fellow, when you again this first fellow starts making the balls, then everything will be corrected. Understand? So that's why we should not stall the pipeline here also. If you stop fetching an instruction, then in the next stage, in the next clock cycle, that instruction decoding will be stopped, execution will be stopped, everything will be stopped. That's why we have to avoid the stalls. Understand? So avoiding the stalls is one important thing. Second thing, so the second, that's it. That is the one thing which you have to always follow. Second one, sir, who will reorder these instructions? As a human being, I know that we have to reorder. Sometimes even I don't know how to reorder because sometimes I mess up all the things by reordering, right? So is there any procedure to do reordering? Generally, who will do reordering? I will tell you, compiler. Okay. So compiler should understand the instructions and their dependencies. Based on the dependencies, example, see, there is a dependency. How that compiler understand the dependencies? If there is something is getting, I mean, someone is reading the R1 and R2, right? There is a read thing. There is a write thing. Write and read are always conflict. Okay. If you are reading something here, right? Sorry, you are writing something and you are reading something. Then these two are conflicting instructions. They should be separated. So compiler will try to insert some instructions so that that conflicting things will be separated. Sometimes your compiler issues no operation. No operation is an instruction specially designed. Okay, assume that let's say your instruction set has no operation. Okay, sir, why this no operation will be there in the instruction set? Example, that instruction set is implementing pipelining. Then in the pipelining, so we have to avoid this kind of stalls, right? Yes, and so of course, I mean that is not related to stalls. I will tell you again. Example, let's say your architecture is supporting pipelining, then such kind of architectures will implement no operation. There will be a separate machine instruction like load, store, everything. So if you have that kind of no operation, then we can avoid this kind of data forwarding, because data forwarding circuit is little bit complex, correct? Assume that let's say you don't want to do data forwarding. What is the alternative strategy you will have? Instruction reordering, correct? If you don't have circuit for data forwarding, then what you can do is insert the dummy instructions between dependency instructions. Example, there are two instructions I1 and I2. There is a dependency like load and add. Then somehow if your compiler inserts no operation instructions, just think about it, no operation, no operation. Then what happens? By that time, when these no operation are executed, by that time the data will be available because of the instruction 1 execution, right? Instruction 1 will be completely executed and it will encounter the write back stage. So by the time when you execute instruction 2, by that time maybe data will be available. So no operations will help you in implementing the simple pipelining. Understand? Sir, why you require no operation? Because of that we are not doing anything, right? So is it not like stalling the pipeline? Yes, it's exactly like stalling the pipeline. Okay, but what is the advantage is, so no data forwarding is required. We are avoiding the data forwarding, so that when there is no data forwarding circuit, then generally the circuits will be simple. Whenever you have a simple pipeline without data forwarding mechanism, then we can go for no operation instructions. This is from your compiler and from instruction set. Second thing, of course, if your hardware is already having this data forwarding circuit, then no operations are generally not required, correct? So this is about all possible ways, right? Remember them. Now finally you understood two things. One is structural hazards, second one data hazards. Now we'll see some of the problems related to data hazards. In the GATE exam, most of the times they give questions related to data hazards and control hazards. I teach control hazards also, but we will see there are a lot of questions from data hazards. What I do is, before going to control hazards, let us solve some problems related to data hazards. Okay.